Yeah, I think we can get started. Before we begin, if someone who's auditing the class or just attending class without registering on KLMS, please let me know if you want to access Mimic 3, because if you don't give me your intention to access Mimic 3, the MIT people are gonna have a hard, they're gonna get confused, because I've already handed them the list of attendance of this class, and if someone who's auditing the class requests access, they're probably gonna know that you are not on the list that I handed to them. So please let me know. All right. All right. So still, we are going to continue from the last time. So just as a reminder, we talked about K-mimic for quite some time, and after that, I've established the task, which is readmission prediction. So we looked at the CMS webpage and then tried to get a feel of the background why this is an important task, readmission prediction. And as I said, the goal was to predict whether the patient will. All right, I'm going to mute everybody. Right. Again, so the goal was to predict whether the patient will return to the hospital again in 30 days. Specifically, it was for patients who had trouble with mostly cardiovascular systems, like heart failure or pneumonia, or one other thing was like arthroplasty surgery, which is related to your knee. So there were certain. So it wasn't like for all patients. It was patients for 6 specific diseases or 6 specific problems who were admitted and then discharged. And then the program, or this HRRP program, was to encourage or to monitor if those patients who were discharged don't return to the hospital back again in 30 days. So, but yeah. I mean, but the task itself could be redefined as we see fit. But just wanted to tell you that there is a solid background as to why we're doing this. And then we talked about inclusion/exclusion criteria for some time, especially with the randomized clinical trial, 임상실험. So as I said, designing the criteria, inclusion/exclusion criteria, requires a lot of domain knowledge and expertise. So it's not something we can do, but I've briefly mentioned that we might be able to train a machine learning model that automatically generates the inclusion/exclusion criteria given the description of the study, like the objective of the study. That would be an interesting application. Right, and then we looked at a couple examples to classify positive and negative cases. So I'm just going to skip through that. And also we talked about when would be the ideal time to make the prediction, or when, like how far we want to go back, like how much previous we want to go back, or how much time we want to preserve so that we can make a prediction and then take action. So that was one of the things we also talked about. All right, so now it's time to talk about ICU readmission prediction. So before it was, as I said, hospital level thing. So it was hospital readmission prediction, but now we can slightly shift the focus to the ICU level prediction, which is ICU readmission prediction. So far, any question regarding what we talked about last time? No? Okay, so I'm going to move on then. So task number 2 is ICU readmission prediction. So it is still a readmission prediction, which means that it is a binary task, but the way that you pre-process the data has to change, because the task is now, given the current ICU admission, predict whether the patient will return to the ICU within the same hospital day or not, well, within the same hospital stay or not. So this is the scope now has come to a single hospital stay. Before, in the hospital readmission prediction, the scope was on the lifetime of the patient. So we were focusing on a single patient, but now we're focusing on a single hospital stay. And why do we do this? So as I said, there is no law or government program for this, but simply because this is a task that we can do based on ICU records. So it is something that we can do with any ICU records, actually, because I've already briefly talked about this. So EICU dataset, we've already established that given a EICU CSV files, we can reconstruct this type of admission pattern, or this type of admission pattern, where the blue strip is the hospital stay and the red strip is the ICU stay. So 병원에 들어간 다음에 이제 다시 처음부터 중환자실 가는 게 아니라 병원 갔다가 중환자실 갔다가 다시 나와서 병원을 나온 거니까, 네, 이제 빨간 게 ICU고 파란 게 병원입니다. 그래서 so this is possible. This is possible. As I said, this is not possible. So how EICU dataset is de-identified is that they don't want us, the users, to reconstruct a timeline of a single patient. So they don't want us to, like, backtrace who went to the hospital, like at which point, and then again at which point, and again at which point in their lifetime. So that's why we cannot reconstruct this type of patient timeline given EICU dataset. Mimic3, we can do that. So given Mimic3, we can reconstruct this kind of thing, but given EICU, we can't. So that's why we cannot do hospital readmission prediction. So in order to do hospital readmission prediction, we need to reconstruct this patient timeline and then decide whether a patient is a positive case or a negative case, whether the patient was readmitted or not. So unfortunately, on EICU, we can't do that. So, but what we can do is focus on a single blue strip. So focus on a single hospital visit, and then try to do something based on that visit, which is the ICU readmission prediction. So that is the motivation. And as I said, if you are interested in like transfer learning or multi-site studies, like multi-site being like multiple hospital, basically. So if you want to use both Mimic3 and EICU at the same time, if you want to merge their data set, or if you want to do like transfer learning or whatever, then you need to define a single task that is applicable to both data sets. So that is why we can't do hospital readmission prediction as a common task, because EICU, we can't do this. But for ICU readmission task, we can. So we're going to talk about this kind of thing in the future, by the end of this semester, when we talk about federated learning, 연합학습. So that's where multi-site studies or transfer learning actually comes into play. All right, so hopefully you guys remember this detail of the two data sets. So okay, example one. So based on this information, this single red ICU admission record, did this patient revisit ICU within the same hospital day? So given this, did this patient revisit ICU within the same blue strip? And the answer is obviously no, because there's only one red strip here. How about this one? Based on this, did this patient revisit with ICU within the same hospital strip? So in this case, we are going to use this. We're going to feed this red information to the model, and then to predict whether the patient was visited ICU again within the same hospital stay within the same blue strip. In this case, of course, the answer is yes. So when you, if the project becomes ICU readmission prediction, then you need to reconstruct this blue strip and the red strip, and then decide who becomes a positive case and who becomes a negative case. So you need to decide. I mean, you need to write the code to do that. So that's why all of these details are important. All right. So based on this information, did this patient revisit? So based on this, we did see this red thing. So it is this guy did revisit ICU within the same blue strip. But in this case, when you're focusing on this time step, obviously the answer is no. And example 3. So this doesn't apply to EICU, but just as a just for technicality, just to be complete. So suppose that we're doing this with Mimic 3, and that we reconstructed this patient lifetime, lifelong experience. And so the question is, given this read information, did this patient revisit the ICU within the same hospital stay? And the answer is, of course, no, because there was a chat. Yeah, obviously, yeah. The answer is no. So 우성님 맞습니다. Because this blue strip represents a single hospital visit. So this patient did revisit ICU again in the future, but not within the same hospital stay. So technically, so obviously, when you encounter this type of patient or this type of admission pattern, and you want to do ICU readmission prediction, this case, you need to say no. So please think about the detail when I do release the project spec. These kind of details would be really important. So, and constructing the proper case, constructing the proper positive negative cases, or constructing the proper training set and the validation set and test set, is it's an essential, it's a vital step towards predictive healthcare. So if you're, for example, if you do that, if you mess that up, if you somehow make a mistake while constructing the cohort, your training set, and your model somehow predicts really well, then, but it is obviously a wrong result. So there is no guarantee that it would perform well on the actual reality when you deploy it on the hospital. So carefully constructing the cohort or the training set is a vital step. Maybe one day, maybe we can automate this with machine learning, which is another thing that I might be interested in. Like constructing the cohort, this takes a lot of time, and this takes a lot of effort, and a lot of things could go wrong because you are writing the code, and there's a lot of features, a lot of tables that you need to attend to. So it's obviously there could be a lot of mistakes, and I did see a lot of mistakes when I opened this course last spring in 2020. And back then, the project that was given to the student was mortality prediction. So it was not that different from this type of thing, but so mortality prediction usually it is a good idea to use like the first 12 hours after the hospital admission. So because the patient usually dies within the ICU or within the hospital stay, but we want to alarm the doctors as soon as possible. So we only use like first 24 hours worth of amount of records, or maybe even first 12 hours amount of records. So there's like certain timestamp involved operations that you need to take care when you're writing code. And the result was that a lot of students actually did make a lot of mistakes. So yeah, it is really hard to nail this, get this complete like without any errors. Really difficult for the first timers. So someday maybe one of the students, one of you guys, can try to train a machine learning model that automatically constructs your training set given an objective. Like you say, I want to do hospital readmission prediction with certain criteria and certain inclusion criteria and certain exclusion criteria, and then maybe the computer or your machine learning model will understand your command and automatically extract patients or patient records for you to use as a training set. Yeah, that would be a very interesting task. I think it would be even more difficult than being automatically generating inclusion exclusion criteria, but I think it's a worthy challenge. Question: I don't really understand why this can be a machine learning problem, not a rule-based problem. That is a good question. That is a very good question. So if you want to solve this problem in a rule-based manner, which is certainly possible, then we need a program that really completely understands the given EHR data set. So for example, let's say that we want to automatically build a hospital readmission prediction training set using Mimic 3. Then we need a program that already understands Mimic 3, how many tables there are, how many, what are the features within each tables are, and I mean the features being the columns, and how the timestamps are managed. So if someone who has already that kind of expert knowledge on Mimic 3, then that person can write a rule-based program where the user interface says what kind of. Yeah, I'm not sure even that would be possible, because there could be a million different tasks. It's not just readmission prediction task, but it could be any task, like heart failure prediction or yeah, the program needs to be really, really general. So like if you are an expert in Mimic 3 and you also at the same time you understand a lot of healthcare problems or clinical problems, then I as a client can come to you, to the expert, and say, I want to do mortality prediction with Mimic 3, and I want to use 12 hours amount of records after the first time hospital admission. Then that expert can understand what I mean and then write a program to extract relevant or appropriate training set. So what I said when I said that we might be able to train a machine learning model to do that, I said that what I meant is we might be able to train a machine learning model that mimics that expert behavior. I'm not sure if rule-based programs can do that. Maybe we can write a rule-based program for a specific task. Like there's a program for hospital readmission prediction. So that program can only generate training set for hospital readmission prediction, and we could change the parameters, how many hours amount of records we want to use, or whether we want to do 30-day readmission or 60-day readmission. Like that kind of parameter could be changeable. So that I could imagine someone being able to write that specific readmission prediction cohort construction program. But I'm not sure if there could be a general purpose program for any type of task, any type of prediction task, a program that can automatically generate training set for any type of prediction task. So that might be a machine learning problem. Hope this answers your question. All right, we'll move on. But that was a really, really great question. All right. There was another example. So based on this, yeah, this is just another fake example. So given this information, did this patient revisit the ICU within the same hospital stay? And the answer is, of course, yes, because the blue bar continues. The blue strip continues. So this patient did end up back in the ICU intensive care unit after this one. So this is, of course, yes. The same issue arises, which is how much previous do we want to go? So in order to predict this, so at this particular time point, we want to predict whether the patient will revisit ICU again within the same hospital stay. And so we want to predict this. And in order to predict this, we don't have to limit ourselves to use this amount, this record only. We could go back to the entire thing. Like we could use the first ICU admission, ICU stay records as well, or maybe even before that, like just starting from the time when the patient was admitted to the hospital to begin with. So we might be able to use entire thing. Or if we want to go even further back, we might be able to use, like if we were to use Mimic 3, then we might be able to use a previous hospital visit records as well. So there is no rule against using, like really using information from the past. But then it's probably unlikely that information from the previous hospital visit would be relevant to predicting this event, because it's probably, something went wrong here or something went wrong here, so that's why the patient is ended back up in the ICU So it's probably something that happened within this time frame. So we don't, probably not a good idea to go back all the way back to like a year ago or 2 years ago, 3 years ago. And again, as I said, so it's the same rule applies. Need time for taking action. So we don't want to use, so when we are constructing the data set, we don't want to use the entire to the like the very last event or very last record from the previous ICU stay, because then we are leaving no room for taking countermeasures or actions for preventing this readmission. So we don't want, we don't want to use like to the very end. We want to probably reserve some room, and the question becomes like, how much time do we preserve? How much time, like how early do we want to raise the alarm? So that's another question that we need to think about when we are thinking about the task or constructing the training set. And usually it's not us who decides, it's the doctors who are or emergency department doctors or ICU doctors. They have a lot of knowledge, so they probably have a good idea how much information we want to leave as like an extra room. So yeah, so if you paid attention, then you probably would understand that both hospital readmission prediction and ICU readmission prediction, they're more or less pretty much the same. It's just the difference is that whether the scope lies in a single patient or scope lies within a single hospital stay, and the rest is more or less the same. The thing that we need to think about, like these factors, and like the simply counting based on the timeline, that characteristic is more or less the same. All right, so moving on. So that wraps up the readmission prediction and different patterns, how different admission patterns are classified into positive or negative cases. So if there are no questions, I will go to the actual more implementation related stuff. So data preprocessing. All right, so I'm not sure if we're gonna be able to cover until MapReduce today. Actually that would be part 2 of predictive modeling, but hopefully we can finish workflow examples. So what we're gonna do is we're gonna follow step by step which table that we want to focus on, and within each table, which column or which feature we want to use when we want to construct a training set for readmission prediction. So we're going to assume that the task is readmission prediction. I think it was hospital. Yeah, so the task is hospital readmission prediction. And when this is given as a task, how we want to approach the CSV files. Hopefully some of you already have downloaded the CSV files on your local hard drive. So you probably took a look at how they look like. It's just a bunch of CSV tables, and that's it. So it might be it might be hard for first timers to imagine how you would handle all those different tables and then construct a training set. So we're just gonna go step by step how we would do that. So data preprocessing depends on information you want to use and model you want to use. So it's not just the task. Like if given a task, we can start preprocessing the data, but that depends on what information. So whether you want to use medication codes, or whether you want to use procedure codes, or whether you want to use like lab tests, or sorry about that, excuse me. So whether you want to use lab tests like blood pressure or body temperature, or that kind of stuff. So it completely depends on what kind of information you want to use. And again, it depends on what model you want to use. So in the future, I'm going to talk about two classical models. So which one is logistic regression, which is a linear model, but still used widely today, to this day, because of this simplicity and ease of analysis, statistical analysis. So when you use logistic regression to predict readmission, hospital readmission, and when you use, for example, RNN to predict hospital readmission, you need to pre-process the data differently, obviously, right? So we're just going to cover those two cases. All right, so the question is, so as I said, the task is hospital readmission prediction. So based on this information, will this patient visit the hospital again? And just as a reminder, there were 20-something, 25 or 26 different tables in Mimic 3. So again, some are admission related or some are hospital level things like admission table, call out table, CPT events, diagnosis events, lab events, patients table, prescriptions. Like these are related to hospital level, like things that occur or events that occur in the hospital level. And then these tables, these 8 tables specifically, are ICU related. So these 8 tables record or store events that only occur while the patient is in the intensive care unit. So charts, like, you know, when you're in the ICU, physicians, so doctors or nurses, it's basically your caretakers. They come to you maybe every 8 hours or every 4 hours, and then check on your status, and then write something on the chart. You know, 차트에 뭘 쓰잖아요. 이렇게 글로 이렇게 뭐 이렇게 뭐 지금은 불편한 점이 있다, 뭐 무슨 뭐 고통 호소, 뭐 열이 내렸다, 뭐 이런 걸 이제 쓰잖아요. So those kind of information goes into chart events. So if you have looked at the CSV files of Mimic 3, you would notice that chart events it's a gigantic CSV file. So the entire data set, if I remember correctly, the entire Mimic 3 is about 40 gigabytes or something. And among them, about 20 to 30 gigabytes are in here in chart events. So this consists of about 100 million rows. 그러니까 이제 몇억 개, 그러니까 이 테이블이니까 여기 한 로우가 한 몇억 개인지 몇십억 개인지 기억이 안 나는데 하여튼 억 단위가 넘어요. 100% 이제 억 단위가 넘어서 그럴 수밖에 없는 게 요 안에 이제 환자가 이제 ICU에 중환자실에 들어가면은 시도 때도 없이 계속 체크를 하면서 몇 시간에 한 번씩 계속 이거를 체크를 하거든요. 이제 환자의 온도가 뭐죠? 그 체온이 몇이었냐, 뭐 그 호흡수, 이제 1분에 호흡 몇 번 하냐, 1분에 뭐 맥박 몇 번 뛰냐, 뭐 산소 포화도 이렇게 그 엄지에다가 이렇게 꼽아 놓잖아요. 혹시 뭐 보셨는지 모르겠는데 그 중환자실 환자들을 엄지에 뭐 이렇게 물려 놓잖아요. 그게 그 손톱 밑에 이걸 보면서 이 사람의 산소 포화도를 보는 거예요. 산소 포화도가 뭐 95다, 90이다, 80%다, 뭐 이런 걸 보는, 뭐 그런 식으로 이제 계속해서 뭔가 계속 그 사람한테 기계적으로 뭔가 이 센서들을 물려놓고서는 계속 이 모니터링을 하기 때문에 그게 뭐 1분 간격, 5분 간격으로 계속 그 기계에 들어가거든요, 그 정보가. 그래서 하여튼 한 번 이 환자가 중환자실에 들어가면은 그 쌓이는 정보의 양이 어마어마해요. 그렇기 때문에 이 차트 이벤트에 담기는 정보가 뭐 몇십 기가치, 몇억 건이 되는 거고, 그래서 그거를 잘 활용하는 게 관건입니다. 왜냐하면 이제 우리가 중환자실 관련돼서 뭐 중환자실에서의 뭐 사망 예측을 한다. 그럼 당연히 이 정보가 굉장히 중요하겠죠. 네, 뭐 이 사람의 뭐 산소 포화도가 떨어지고 있다던가, 뭐 호흡이 떨어지고 있다던가, 이런 것들이 다 어떤 사망으로 이르는 어떤 그 사인이니까. 그래서 근데 이게 몇억 건이 되기 때문에 이걸 단순히 뭐 판다스에 올린다, 이게 불가능해요. 판다스에다가 몇십 기가짜리에 올리려면은 노트북에선 불가능하겠죠. So as I was speaking in English, as I was speaking in Korean, if you want to do something related to ICU level thing, like whether trying to predict whether the patient dies within the ICU stay, so that would be a mortality prediction. If you want to do that kind of task, then you need to really care about how you extract relevant information from this table, which is like 20-something gigabytes. So if you are used to using pandas, the data frame, you probably won't be able to load this up on data frame using your laptop. You need like a workstation level computer to be able to do that. So if you are familiar with Spark or MapReduce, then you might have an easier time pre-processing this. So if you have like multiple computers all like hooked up using Spark or Hadoop, then you can divide this into several like pieces and then distribute it into multiple computers, and then write MapReduce codes or like Spark codes to pre-process the data. So that would really save you a lot of time. But usually all the other tables, like all the other tables are usually, if they're large, then it would be like several gigabytes of data, or that's it. So you can just iterate, like using for loop. You can just go one line by one line and then just extract the information. So yeah, so chart events is probably the most important thing in these 8 things, and then probably the next important thing is note events. So not all information are structured, like respiratory rate, so like 호흡수 or heart rate, 맥박수. Those are structured information, so they are stored in the machine automatically. But all the other things, like your complaints, 뭐 불편 사항, 아니면 or any special events, 특이 사항, something that is not really easy to store in a structured format, it must be stored in a textual format. So this is unstructured text, and this is why one of the reasons why EHR data is it's like a multimodal data set, or heterogeneous multimodal data set. So if you're interested, or if you're like really familiar with NLP techniques, when you're doing like mortality prediction as a project, you might want to use this information as well. But it's probably won't be easy to pre-process both chart events and note events at the same time. I think there was a question. 병원에서도 워치 같은 웨어러블 디바이스로 환자 상태를 추적하고 할 수 있을 것 같은데 그런 시도는 데이터도 있을까요? So very good question. People these days do wear a lot of smart devices like Apple Watch or Fitbit or Galaxy Watch, and those kind of devices do actually store your heart rate, your body temperature. I think they do have a couple more functionalities, but so they store that kind of information throughout the entire like day if you so want to, and then you can access your information, using a health app or whatever. I think Apple Watch has like Apple Watch app, and then you can see your, I don't know, like heart rate pattern or whatever throughout the day. So you can, if you want to, you can provide that information to the hospital when you're when you go to the hospital for medical checkup, or if you have some kind of cardiovascular problem, then the information gathered or collected by the smartwatches might be helpful for the doctors to make a better diagnosis. But I don't think it's a norm. I don't think people usually do that. So you can technically do that, but I don't think a lot of people do that, because maybe people would consider that a private information. So that's when you're using external, like third-party smartwatches or smart devices. But hospitals do. So if the doctor thinks that you are if you require it, then they might give you some kind of sensors. So it's not like Apple Watch or something, but like a heart monitor. They might give you a heart like monitor device, and then which you always have to wear around your heart, so that sensor can collect data, and then when you revisit back to the hospital, maybe after a couple of days, then they can analyze the records or data collected by that specific sensor. So for example, if you have arrhythmia being 부정맥, 부정맥이 있으면 이제 심장이 뭐 irregular하게 뛰는 거잖아요. 이렇게 원래는 이렇게 딱딱딱 뛰어야 되는데 뭐 딱따닥 딱딱따닥 뭐 이런 식으로 이제 뛰는 거니까 이제 굉장히 위험한 위험한 증상인데, 그런 게 있으면은 이제 그걸 병원에 가서 내가 이제 부정맥이 있다 그러면 이제 선생님이 막 이제 뭐 테스트를 해보고 여러 가지 해본 다음에 이 사람 좀 심각하다 그러면 이제 그 부정맥을 체크할 수 있는 모니터 같은 거를 줄 수도 있어요. 이제 그 이제 맨날 차고 다니는 거죠. 가슴팍에다가 또는 어딘가에 이제 차고 다니면서 이제 매일매일 그리고 이제 며칠 차고 다니면서 약 먹고 이러면서 이제 이제 센서가 이제 이걸 계속 체크를 하는 거죠. 그러면서 계속해서 이제 컬렉션을 하고, 그다음 나중에 이제 약 먹고 뭐 며칠 있다, 뭐 일주일 후 또는 2주일 후에 이제 병원 다시 가면은 그 센서를 뜯어다가 이제 뭐 필요하면 이제 의사 선생님이 또 분석을 해보실 수 있겠죠. 그래서 이제 그런 거는 가능합니다. 근데 그런 데이터가 있느냐? So are there such data, like wearable device produce data? There, as far as I know, I don't think there's an open source data for that. So, I mean, if you could imagine if Apple releases an open source data set which collected from individual Apple users, that would bring a catastrophic repercussion, because that means that Apple is collecting your data and then they're open sourcing the data set, which is probably not the best idea for Apple. I mean, especially for Apple, because Apple is very, very they're very keen to protect user privacy. So you've heard news that they don't even cooperate with the FBI. So FBI had to crack iPhone on their own using their own effort. So yeah, Apple would never do that. I don't think Fitbit would do that either. So I don't think any private vendors that have like business model using wearable devices would ever open source open source records collected from multiple devices, because first of all, it's their asset, so you don't want to release your asset, and second of all, it's private information, so it's really easy to get into trouble. All right, so maybe someday, yeah, maybe, I don't know. Yeah, I'm not sure if maybe even someday that would happen. But anyway, so what I was trying to say is that there are some alternatives. So if you're interested in time series data, like like heart rate data or whatever, there are alternatives. So there is an EKG data set, open source, again from the Mimic people. So it's called Mimic Wave Data, or was it Mimic Waveform? Give me just a second just to check. Yeah, it's called Mimic Waveform Database. So it's probably released by the MIT people, and it's waveform dataset. So it contains EKG or ECG raw data. So 이제 심전도를 그대로 raw 데이터 그대로 이제 릴리스한 게 있습니다. 그래서 그게 어떻게 보면 사실상 가장 좋은 센서 데이터죠. 심전도 하려면 다 이렇게 센서 붙이고 하니까. 이제 심전도 데이터가 실제로 릴리스가 많이 돼 있어요. 심전도 데이터는 심지어 그거 보고서 누군지 맞추는 게 어렵기 때문에 이게 이 프라이버시 프로텍션도 굉장히 잘 되는 편이고, 그래서 심전도 데이터를 릴리스하는 경우는 꽤 많고, 그건 이제 피지오넷에 가보시면 그 종류가 되게 많아요. 이제 뭐 MIT 말고도 미믹 말고도 이제 그 심전도 데이터셋이 꽤 있으니까 궁금하시거나 뭐 이제 나는 센서 데이터나 타임 시리즈 데이터에 관심이 있다 그러면 이제 심전도나 아니면 뇌파 EEG라고 해서 뇌파 데이터, 그런 거를 좀 사용을 해보시는 것도 좋습니다. Alright, so yeah, as I said, if you're interested in processing or using building machine learning models based on time series records like ECG or EEG being brain something related to your brain signals. So yeah, there are open source data sets both for EKG and EEG, so you could start from there. All right, so back to the material. Right, so please keep in mind that you have to use both. So actually you have to use all of them in order to build a complete predictive model for hospital readmission. But first of all, we're gonna you need to understand. So as I said, if you want to build a predictive model, you need to first decide which information you want to use and which model you want to use. But some are optional. Among all these tables, some are optional and some are a mandatory. For example, you need to really you must go through the patients and admissions table in order to construct this blue and red line, this strip. And this is the beginning, because in order to distinguish between the positive case and negative case, first you need to rebuild this blue and red strip. So that's where you need the patient's table and the admissions table and the ICU stays table, because this table stores the information related to when the patient was admitted to the ICU and when the patient was discharged from the ICU. So you need to go through at least patients and admissions in ICU stays table. So something like that. So some tables you must go through, some tables are optional. For example, if you want to use diagnosis information, then you might want to use this table. But if you're not interested in using diagnosis, then there's no need for you to go through this. So that's up to you. In this case, so this is hospital readmission. I'm going to go through a very simple pre-processing steps where you use the diagnosis information, prescription, so the drug information, and the procedures information. So the procedure being 시술, so 뭐 수술이든 뭐 엑스레이를 찍었든 깁스를 했든 뭐 그런 것들. 어떤 뭐 처치죠, 처치. So we're going to use three information: diagnosis, prescriptions, procedures, and the meta information will be collected from patients' admissions. And just to keep things simple, we're not going to use any of these information. So again, the task is hospital readmission. So using this entire blue strip, so anything that happened within this blue strip, including this red strip, the task is to use any information within the blue strip and then predict whether this patient will return to the hospital within 30 days. So in this case, this patient is a negative case. But anyway, we don't know that. We need to. The model doesn't know that. So the model only knows any event that happened within this blue frame, this blue strip. And as I said, as a practice, we're not going to use this information because it's just too much. Usually the three things that are always there in all EHR datasets are diagnosis codes, prescription codes, the medication codes, and the procedure codes. These three information are usually always there, regardless of which hospital you're working with, regardless of which EHR system or solution you're working with. It's always there. So we're going to use these three information. And actually, these information are also always there, even for outpatient records. So this is an inpatient record. inpatient 이제 내원 입원 환자. 그러니까 병원에 와서 일단 입원을 해서 하루 이상 병상에 머무르면 그건 입원 환자고, 그게 아니라 병원에 와서 뭐 진단받고 처방받고 가면은 이제 우리가 보통 뭐 감기 환자들처럼 그러면 이제 그건 외래 환자거든요. 이제 외래 환자가 아웃페이션트고 입원 환자가 인페이션트고, 이제 인페이션트가 이제 심각하면은 ICU 페이션트가 될 수가 있는 거고 뭐 그런 건데. So I was just talking about the concept of outpatient and inpatient. So outpatient is a patient, for example, if you have a cold and then you go to the hospital, you get diagnosed, and then you get prescription and then you leave, that's outpatient. If you stay within the hospital bed for more than 1 day, then you are inpatient. So obviously, inpatients generate more diverse records. That would be obvious, right? Because outpatient, if you are an outpatient, there's not much time for you to generate interesting records like chart events or ICU stays or note events or output events. Like these are all related to ICU records. So if you are an outpatient, you are not going to generate this information. So but if you are an outpatient, you still generate this information: diagnoses, prescriptions, and procedures. They're all this applies to regardless of whether you are inpatient or outpatient. So it is usually a good idea to start with this three, kind of like a pillar information: diagnosis, prescriptions, procedures. All right. So okay, we're gonna go through the actual tables and see how we're gonna collect or extract the information and then rebuild this timeline. All right. So starting with the admissions, because we are interested in building the blue strip here. So in order to build the blue strips, we need to go through the admissions. And if you want to build multiple, so for example, if some patient visited hospital 2 times, then you still need to go through the admissions table and then find out this patient actually did visit hospital 2 times. So that's where So admissions table is where all the event, all that information is stored. So if you look at here, so we're gonna use 1, 2, 3, 4, 5, 6, 7, 8. What is it? 8? Yeah, we're gonna use 8 information. So all these like rows or all these features are relevant to, probably relevant to readmission prediction, more like one way or the other. But we're just gonna use ones that are easy to understand. So subject ID is the patient ID. So that's just, like your 주민등록번호. HADM ID is the unique identifier for each hospital stay. So if you visit hospital one time, then you generate one HADM ID. If you visit hospital 2 times, then you, as a subject ID something, possess or contains 2 unique HADM IDs because you visited the hospital twice. Admission time, discharge time, hopefully this is obvious. So this is when you are admitted to the hospital. This is when you leave the hospital. So these are all timestamps. Admission type, so this is whether you walked into the hospital by yourself or whether you were transferred from the emergency department or whether you're referred to from some other hospital. So there's like certain number of different admission types. Just for fun, we're gonna use marital status and ethnicity. So whether you're single or whether you're divorced, whether you're married or unknown, or I don't know, something. There might be some different types of marriage types these days. Ethnicity, so whether you're Hispanic or Asian or like Black American, white American, or Native American. So this kind of doesn't really apply to Korea because we're more or less the same ethnicity. These days it's changing, but ethnicity is not much of an issue in Korea. But in America, in the United States, this is it's always an issue. And this diagnosis is different from this diagnosis. So this diagnosis is something. It's a summary of all the like complaints and diseases and problems that you went through during your entire stay, during your entire visit, the blue strip. But this diagnosis here is kind of like the reason for visiting the hospital. Like it's like a primary reason. So why you were admitted to the hospital to begin with, whether you were having a shortness of breath or whether you were having a trauma being 외상. So whether you had like a trauma or whether you were, whether you fainted or whatever. There are like, I think there are maybe like dozens of different primary reasons. So all the others, like, so insurance and language, religion, they might be relevant or not, but actually marital status and ethnicity, they might be irrelevant to hospital readmission prediction. Like why would your marital status be relevant or be useful for predicting whether you will revisit the hospital or not? So somewhere like kind of like suspicious. Why like all the features, we are not really completely sure whether they're really useful or not. As a non-expert, it's really hard for us to decide which feature to use and which to not use. So again, if you want to, that kind of feature selection is usually up to domain experts, the actual doctors. So, but since we are using deep learning, or we are interested in deep learning, the spirit is just use as much information as possible. So so that the model can figure out on its own. So, but still, usually for the purpose of increasing the performance or making a lightweight model, we usually do select features anyway. So just if we're on our own, if we don't have the domain expert side by side, then it's just up to us. So we just reasonably to our best effort choose relevant features. So we're just going to choose marital status, ethnicity, and diagnosis, admission type, and these 4 are a must. So I'm going to use a Python Python style data structure. So there's patients. I'm going to define patients as a dictionary. So this is a Python dictionary. By the way, is there anyone here who's not familiar with Python? I did say the prerequisite was Python, and hopefully a lot of people have gone through the previous programming for AI. So All right, so everybody, okay, everybody's familiar. So I'm not going to go through what dictionary is. Okay, so I'm gonna define patients as a dictionary. So this is where all the information is going to be stored in order to reconstruct this blue and red strips. So this, well, not red strips, because we're not going to use ICU related information anyway. So we're only going to reconstruct the blue strip, and we're going to use diagnosis, prescription, and procedures. So we're going to store all the information collected from the red table, the target tables. I'm going to store that in the dictionary, and then later I'm going to convert this dictionary into a vector form in order to feed that into either logistic regression or RNN. But before we vectorize the features, we first need to reconstruct this timeline. That is why we need this kind of like process. But this is not the only, so I'm going to go through this using the dictionary-based example, but just note that this is not the only way to do it. You could just use pandas and then do whatever you want, but I'm just going to use dictionary, which is a bit more intuitive. So within the dictionary, of course, because this is patient's dictionary, so the key would be the subject ID being the unique identifier given for each patient. So that would be the key. And then given a key, that becomes another dictionary. So it's a dictionary of dictionaries, a nested dictionary or nested lookup table, if you will. So the second key, the key for the nested or the internal dictionary would be HADMID, which is the hospital admission unique identifier. So we're just nesting based on the hierarchy being where the patient is at the top, then below the patient there's multiple hospital visits, and then within each visit there's multiple diagnosis codes and procedure codes and whatnot. So the first key is the subject ID, the second key is the hospital admission ID, HADMID, and then within hospital admission, within a single hospital admission, that becomes another dictionary. So it's a triple nested dictionary. So there's a dictionary here, then each patient becomes a dictionary, each hospital admission becomes a dictionary. And this is the final innermost dictionary, is where you store all these information. So not this one, this one, yeah. Admission time, discharge time, admission type, marital status, ethnicity, diagnosis. You store that information into the innermost dictionary. So admit time would become, you store the admission time into admit time. You store discharge time to discharge time. I mean, the field name could be the name of the key could be anything. It's up to you. But I'm just gonna say, I'm just gonna use admit time, discharge time, admit type, marital status, ethnicity, gender. Oh, I forgot to actually talk about gender. All right, that. So first of all, 1, 2, admit time, discharge time, admit type, marital status, ethnicity. So first five information could be collected from this table. And also this one, admit DX. This could also be collected from here. So we map this information to here, we map this information to here, right? So which is simple enough. But gender, something that I want to use as a feature for predicting hospital readmission, gender is not in here. Gender is not here. So we're gonna find where gender is in the next page. And then, as I said, we want to use diagnosis, procedure, prescriptions, and procedures. So we need to prepare a list to store that information. So we're gonna store DX list, where we're gonna store diagnosis, list of diagnoses, because there could be multiple diagnosis codes within one hospital stay. For the same reason, we're gonna prepare a medication list and procedure list, and then we're gonna populate this when we go through diagnosis, prescription, and procedure tables. And then, of course, we need the final label, whether this patient was readmitted to the hospital or not within 30 days. So readmission, we're just going to set that to 0 for now, because we don't know whether the patient was readmitted came back to the hospital or not, as of yet, not yet. So, okay, so far, I hope this is pretty much clear. This, as I said, doesn't have to be a triple nested dictionary. It could be like, structured tuple or named tuple. It could be a named tuple. It could be anything, or it could be, you could start from actually a vectorized, like you could start from the vector itself, like you could use NumPy vector to populate the information. Doesn't matter, but it's just wanted to go over the concept. So hopefully this is all clear. I'm going to move on to the next one. Patients. So actually, gender, the gender that we set for 0 for now. So gender is again, I actually didn't go through the types of features. This is a timestamp feature, so it would be numeric, or it could be date-time object of Python. Admit type, this would more or less likely be a categorical information, categorical features, because there I said, like, you could walk in, you could come from the emergency department, you could be referred to. So at least there's like 3 or 4 different admission types. So you need to convert that into a one-hot vector in the end. So as to vectorize everything. And ethnicity same, marital status same, but the gender is hopefully we can agree that there are 2 genders. So if you want to use more genders, then you could use like 1, 2, 3, or you could use like a vectorized categorical form. But at least in the mimic 3, there are only 2 genders. So there's 0 or 1, or male or female. So we're going to use a binary just code 0 or 1 to represent the gender. And of course, readmission would be also a binary information. You are readmitted or not. So yeah, these are not like, some are strings, some are categorical, some are binary, some are numeric, some are, there is basically a very very heterogeneous multimodal data set. So yeah, as I said, for now, the gender is set to whatever default value, 0. Let's say 0 is male and 1 is female. So we're going to set all the genders to 0 for now when you go through the admissions first. And then when you refer to the patients table, that's where gender information can be found. And you have the subject ID as well. So once you've prepared this triple nested the dictionary for every single patient, which there are about 45,000 patients, I think, or more or less like 50,000 patients. So if you populate this data structure, going through all the admission rows, then you can come back, go to the patients table, and then look up the subject ID from your patient's nested dictionary, the data structure that we just constructed from the previous page. You can look up using the subject ID and then set the gender, the admission gender, to 0 or 1, depending on whether it's male or female. So the code would be for ADM in patient subject ID. So subject ID being, you can copy paste from this field, and then you set ADM gender to 0 or 1. ADM gender being this gender. So it's just a repetition of for loops. So hopefully this is clear. And then we're gonna start populating DX list, RX list, and proc list. So starting from the diagnosis list. So there is a table called diagnosis ICD. I think we've already briefly took a look at this maybe 2 classes ago. The table is really simple. It doesn't contain a lot of different information. It has the row ID, which is the primary key. It has a subject ID, which is a foreign key. So the subject ID is, of course, is a patient ID. And HADM ID is also a foreign key. So HADM ID being the hospital admission ID. So what this table contains or stores is at which hospital stay, which patient received which diagnosis code, and that's it. So this ICD-9 code is actual disease code, like a hypertension or kidney injury or broken bones or cancer or hypertension. I mean, I think hyperlipidemia, something like fever or whatever. I think there are about 10,000 different ICD-9 codes for describing different diseases. Sequence number here is auxiliary information. As I said, you could receive multiple diagnoses from a single hospital stay because you can get sick for many different reasons. So sequence number kind of indicates which is the primary diagnosis code and which is secondary. So if you get like 5 different ICD-9 codes within the same hospital stay, then you have like sequence number 1, 2, 3, 4, 5. But for now, we're going to just disregard that. We're going to ignore this information and only take subject ID, HAM ID as a meta information to go through the lookup table. So the patient's table, you're going to use subject ID from here, HAM ID from here, and then you're going to go through the DX list key And since dxList key is a list, it's a Python list, so you're going to append this information, this varchar information, into that list. So that's basically how you populate the dxList. So you go through all this, every single rows in the diagnosis ID, diagnosis ICD table, and just populate using this form. Same with procedure, because procedures ICD and diagnosis ICD, they have the same schema. It's exactly the same. They're identical. So they have the subject ID, HMID, and then this ICD-9 code is actually not the same ICD-9 code as the diagnosis, because there's diagnosis ICD-9 code and there's procedures ICD-9 code. They're different things. So procedures ICD-9 code, I think there are about some maybe 4,000, 5,000 different ICD-9 codes. So this you can use to populate this list. So patient, subject ID, HMID, proc list. So because this is a procedures list, so you proc list, and then you append this varchar into the ICD-9. You append this information to the list. That's it. Prescriptions are a bit different. Prescriptions, it's a bit more information rich, information heavy. So because prescriptions are, it could be ICU level thing or not. So you can see that there are subject IDs, and then there's HADM ID, so which you've already seen here as well. But there's also ICU stay ID. So some medications are given while you are in the ICU, the intensive care unit, but some medications are given to you while you're in the hospital ward. 그러니까 이제 ICU에 있을 때 약을 주기도 하고, 이 병동에 그냥 입원해 있을 때 주기도 하기 때문에 요 프리스크립션 테이블은 이 하스피털 레벨이기도 하면서 ICU 레벨이에요, 둘 다. 그래서 이제 어떨 때는 ICU 스테이 아이디가 있을 때도 있고 없을 때도 있고, 있으면은 이제 그거는 ICU 있을 때 약을 준 거고, 이게 만약에 널이다, ICU 스테이 아이디가 널이다, 그럼 그거는 이제 병동에 있을 때 준 거고, 그런 겁니다. But we're just gonna treat everything, all our prescriptions as just hospital level things. So we're just gonna ignore ICU stay ID for now, and we're gonna ignore all the start date and end date, because these are actually important information. 그러니까 when as a doctor you prescribe a certain medicine to the patient, you usually specify when to start taking the medicine and when to stop taking the medicine, and how you should take the medicine. Like I think there's route. So whether you should take it orally, whether you should take it intravenously, whether you should take it as a patch on your skin. 이제 이 약으로 먹냐, 경구 투입이냐, 아니면 뭐 피하지방으로 피하지방 그 뭐죠, 그 주사, 그 IV 주사로 넣냐, 아니면 패치로 하냐, 이게 다 다를 수 있잖아요. 그런 거가 이제 라우트가 됩니다. So that kind of information, dosage, like the strength of the medication, these are all very, very relevant, very important information. Unlike the diagnosis and procedure codes, prescriptions come with a lot of like auxiliary information, which might be really relevant to hospital readmission prediction or not. I'm not the doctor, so I can't say, but they might be relevant. But for now, just for the simplicity, we're gonna ignore all the side information. So start date, end date, these product codes, the strength, the dosage, the routes. We're just gonna ignore all these information and just gonna treat prescriptions as this in the same manner as procedures and diagnoses. So we're just gonna take the subject ID, HADM, the drug name, or there's an alternative. So drug. Actually, I could briefly show you the before. I think there was a question. 딕셔너를 사용한 아까 말씀하신 펜더스 로드가 어려운 데이터 처리가 많이 용이해지나요? 질문 두 개가 들어오네. 일단 류도훈님 거부터 설명을 드리자면, 딕셔너리를 사용하면은 일단 딕셔너리를 만들 때 이 로우 바이 로우로 for loop을 돌면서 놀잖아요. 지금 아예 제가 잠깐만 그 로 데이터를 띄워드릴게요. 네. 이거 제 콘솔 화면 보이시나요? 네, 좋습니다. 네. 그러니까 여기서 이제 우리가 actually I should speak English. So the question from Ryu Do-hoon was that if we use this dictionary-like data structure, then would it be easier to pre-process data compared to using pandas. So what I'm trying to show is that if you look at the data sizes. So so chart events is like 33 gigabytes, but we're not going to use chart events. So what we were using is we started from the admissions table. So if you go to the admissions table, basically, when you first construct a triple nested dictionary, you need to go through every single row, like row 2, row 3, row 4, until the end, which is about 60,000 rows. So you go row by row and then populate the triple nested dictionary. So there's no need for you to load the entire CSV file into the pandas data frame. So that's how you save your memory. If you are to use pandas, then you need to load the entire CSV file into the data frame, and this is only 12 megabytes. So because admission is only 12 megabytes, that might be okay. So it's not eating up too much memory. But if you are to use like chart events, or maybe there are some large ones like input events, 2.3 gigabytes, patients 2.5. This is megabyte. Yeah, 3.7 gigabytes. Note events. What else? Yeah, there are some tables that are pretty size heavy. So if you were to use pandas, then you need to load the entire CSV file, and then that's going to say spend a lot of your memory space. But if you were to use data structures like mine, the triple nested dictionary, then all you need to do is just go row by row. So open the file using a file descriptor, and then go row by row, and then just populate the file and populate the data structure, and that's it. So it's going to take more time because you're going through the for loop, but it's going to save memory. So there's an alternative. So yeah, 답을 말씀드리자면은 이게 작은 데이터로 하면은 판다스로 하는 게 더 쉬울 수도 있는데, 이게 그렇지 않고 이 데이터 양이 커지면은 이런 식으로 이제 for loop을 돌거나 아니면 아까 말씀드렸던 스파크를 쓰거나 그렇게 해야 됩니다. 네, 그리고 second question from 이춘경님. ICD-9 코드나 드럭도 categorical 데이터인가요? 종류가 수천 가지가 넘으면 원핫 인코딩하기 어려움이 있을 것 같은 이런 데이터 어떻게 좋은 질문이에요. 네, it's a very good question. The question was that the ICD-9 codes and drug codes, are they categorical? So if there are 10,000 different ICD-9 codes or 10,000 different drug codes, then it's probably we have to actually encode them into one hot encoding, because they are different codes. So you usually, if you are familiar with PyTorch, then you end up using lookup table. So, but this kind of this is more related to using RNN. But if you are using logistic regression or some simple model, yeah, I can get back. Let me get back to the details of the lookup table when we talk about the modeling part. But so the question is valid. If the IC9 codes or drug codes there are like 10,000 or maybe 20,000 different codes, then how should we treat them? They should be treated as one-hot encoding. They are actually exactly like the words in the NLP vocabulary. Like if you are familiar with BERT uses 30,000 tokens, unique tokens as its vocabulary. So it's the same deal. You have like 10,000 different diagnosis codes, 10,000 different prescription codes, 10,000 different procedure codes, and then they comprise an entire vocabulary in this data set. So 30,000 different codes. So, and when you do treat them as like vocabs, then you need to use lookup table. Otherwise, you need to. It's not all okay. So yeah, this again, I'll get to this detail when in the modeling part. But it's not always the case. You can use lookup table. So sometimes you must use a one-hot encoding and then convert that into like a lower dimensional latent embedding. So you need like a very large sparse matrix. So it's always a problem. Like saving the VRAM is always a problem. Hope that answers your question. 이춘경님 혹시 답이 되셨나요? 네, 좋습니다. Question from 성진 Park. Mimic 3에는 drug 같은 것들이 unseen 데이터의 확률이 적은 편인가요? 그게 무슨 의미인가요? 미싱 데이터를 말씀하시는 건가요? 아니면 뭐 드럭 같은 것들이 새로 나와서 이제 내가 처음 본 드럭들이 갑자기 들어온다거나 뭐 그런 걸 얘기하시는 건가요? 네. Okay, so this is also a very good question. So the question was that can in mimicry can there be cases where the model sees brand new drugs that it hasn't been trained on? And the answer is obviously yes, because new drugs are developed every single day, and not every single day, but so for example, if you train your model on data set spanning from 2000 to 2020, like 20 years worth of data. You train your model on 20 years of data, and you start feeding new data from 2021, then it is kind of unlikely there would be new drugs, like new unseen medications coming into the model for inference. But maybe 5 years later, like, in 5 years is a long enough time for new drugs to be developed. So if you have a model trained from 2000 to 2020, and then you give a record from 2025, then there must be new drugs that the model has been trained on. So that would be like an out of vocab situation. So that happens. So sometimes we might want to use the ingredients of the drug rather than actual drug name, like acetaminophen is Tylenol. So but Tylenol is a product name. Tylenol is drug developed by Bayer. Bayer 생각했나요? And anyway, so Tylenol is a product, 상품 이름이죠. 상품이요, product name. But the acetaminophen is the ingredient name. So we might want to use acetaminophen as a drug name rather than Tylenol itself. So then there might be, but new ingredients are developed less frequently than new products, right? So that might be a good idea. So I was actually going to show you guys the prescription table. So actually, let's go with the diagnosis first. So diagnosis, as I said, it's a very simple table. So there's only 1, 2, 3, 4, 5 features or 5 columns, and the ICD-9 code, like 40301, it's unlegible to people. So we can't understand what 40301 is. So as I said, we need to look up to go to the ICD-9 okay. So all right. So we need to go to the descriptions table to really understand what this is. So we're gonna. So 40301 is hypertensive chronic kidney disease, malignant with chronic kidney disease, stage 5 or whatever, yada yada yada. So there's a very long description for this. So diagnosis code and this is what diagnosis code looks like. But the same goes with procedures ICD. Both look exactly like the same. So the code themselves are just numbers. So you can simply convert this number to a integer, like you have a 1-hot encoding, or you can actually map this to the actual description and then map that to 1-hot encoding. It's up to you, but the things are a bit different with the prescriptions. So prescriptions, there is no code. It's just string. So before diagnosis and procedure, it was number, right? It was a numeric code. But now the drug, if you go to drug here, these are actual drugs, like heparin sodium, tacrolimus, mycophenolate mofetil, I'm not sure what that is, nitroglycerin, insulin, atropine sulfate. So these are these drug names. So you need to actually, when you're populating the RX list, you need to use this string to populate, or actually you can convert the string into an integer, like 1-hot encoding, and then populate the RX list with that number, with the integer, the 1-hot encoded integer. And as you see here, these are more or less probably ingredient name rather than product names. Like what I'm pretty sure there's that's because D5W is just water with sugar in it. So there must be tons of different products with sugary water. There are alternatives. You could use this. You could use this drug column. You could use the drug column and then take the strings as the drug value, or you could use something called formulary drug CD, which is a bit more codified versions of drugs, which is like 420 warp 0. Warp 0, like furosemide becomes 420, and warfarin becomes warp 0. Tacrolimus becomes TACR, TACR 5. Atropine sulfate becomes atro 1I. So it's a bit more abbreviated form. So you could use this instead. So that's what I wanted to tell you guys. So I'm gonna go back to the original slide. Right, so that's formula drug CD here. So you could use the drug values, or you could use formula drug CD, whichever you want, whichever has the list missing values actually, because sometimes it's not always the case. The doctors or the nurses or the IQ workers enter the complete information into the EHR system. So sometimes drug value might be missing. Sometimes formula drug CD might be null value. So you might want to use whichever has least amount of null values, and you choose one, and then you populate the RX list, like append drug or append formula drug CD. All right. So given this, so once you've gone through all the tables, so tables, admissions, patients, diagnosis ICD, procedures ICD, prescriptions, then you have the entire thing ready. And now what you need to do is, in order to distinguish who becomes a positive sample and who becomes a negative sample for hospital readmission prediction, you need to sort the order of admissions for individual patients first. So if you look up a certain patient using a certain subject ID, the 주민번호, then you will have a list of, or you will have a dictionary of admissions. So because, as I said, the original data structure is patients look up, so patient parenthesis, no, not parenthesis. Anyway, given a patient key, that becomes a dictionary. So when you look up a certain patient with their subject ID, you see a dictionary of different admission IDs. So you need to sort the admission IDs by their admission time. So that's why. So this is necessary in order to reconstruct this timeline. So for the triple nested dictionary, you don't know which happened before and which happened after. You just have a set of admission records, and that's it. So you need to actually sort the admissions based on their admission time, so that you can construct this timeline, and then you can classify or distinguish whether a patient readmitted to the hospital within 30 days or not. So you need to do, so in order to do that, you need to sort the admissions by their admit time. So you could use so this would be like a Python code for doing that. So you need to reconstruct you need to populate or create an admission list. So, and doing so would be like sorted. You go through the patient ID, subject ID, and then you iter items, and then you go through all the admissions, and then you sort the admissions based on their admission time, and then you construct a list of admissions. So using admit list to iterate through the patient subject ID in temporal order. So temporal order, this is the important thing. Then you set patient subject ID, admission ID, which is the using the triple nested dictionary, and finally the readmission key. You set this to 1 if the gap between the current admission list item, and the next item is less than or equal to 30 days. So you construct this based on this. Based on this, you construct admission list, and then you iterate through the admission list. And if the gap between two consecutive items is less than or equal to 30 days, you go to the corresponding admission and then set the readmission label to 1, and that's it. So the final output would be a list of admission objects, regardless of the subject ID. So once you have all this, once you have the triple nested dictionary with all information populated, including the readmission label, once you have that, then you need to finally you need to convert that to a list of admission objects. So just because this task, this hospital readmission task is admission hospital level based. So it's admission based. So you no longer need to care about the patient timeline, because now the test is based on a single hospital admission. So you don't need to care about whether a single patient admitted, like visited hospital twice or 3 times in their lifetime. That becomes unnecessary anymore. So once you have all the information. So the reason that we constructed the triple nested dictionary to begin with was only because we wanted to populate readmission label. Otherwise, we can't do that. So we went through all the trouble of the triple nested dictionary only to set the labels correctly to either 0 or 1. And once we have done that, then we just need to dump that information into a list of admission objects. So this becomes your training set. So yeah, so now the subject ID is no longer an issue. All that's important. All that is important is the HA-DIM ID, and based on a single HA-DIM ID, you predict whether the patient will return to the hospital within 30 days or not. All right. So yeah, for ICU readmission prediction, what time is it now? It's 54. So let me see. All right, I think we can. Yeah, I'm just gonna briefly go through this, and then if necessary, I'm gonna recap this next Tuesday. So far we talked about how to pre-process data using hospital readmission prediction task. But if we are to focus on ICU readmission prediction task, then you could probably imagine what you need to do. So the task is based on this information. So if the task is ICU readmission prediction, we probably don't need to care about the patient timeline. Correct? Before, when we were talking about hospital readmission prediction, we needed to reconstruct the entire patient timeline, the patient lifetime visit pattern, in order to make the label. But if we are to focus on ICU readmission, there's no need to focus on patient level visit record or visit pattern, because all we are interested in is a single hospital stay. So hope this is clear to everybody, because this is kind of an abstract idea. So again, so in this case, we are gonna just for the sake of simplicity, we're just gonna focus on single ICU stay. We're gonna use single ICU stay record, and then try to predict whether this patient, within this blue strip, there would be another red strip. So based on this information, we're going to predict whether there would be another red strip within this blue strip. And we're going to use this information here, chart events in ICU stays. So we're not going to use all these hospital level things, because just for the sake of simplicity, we're gonna focus on this information. But in reality, you probably want to use all information, including this part as well, in order to predict the future ICU admission. But for simplicity, for just describing the pre-processing steps, I'm gonna exclude information that happens from here, which would be like like diagnosis or prescriptions. That might happen within here. I'm just gonna ignore that. I'm just gonna focus on this part, and that's why I'm using only ICU stays and chart events. Actually, yeah, I don't think we have enough time to go through this. So yeah, that would be the premise. So we've gone through the hospital readmission prediction task and how to pre-process data in a very, hopefully in a rigorous detail, so that everybody understands, everybody has an idea. If they're asked to construct a training set for hospital readmission prediction task, they can do this now. So hopefully that's the case. And since we've gone through this, the ICU readmission prediction task pre-processing is more or less the same. But so I'm gonna end today's class here and then come back to this in next Tuesday. So any question? Any question related to the hospital readmission prediction, the pre-processing, and the triple nested dictionary, whether it's too complex or not? Right. Okay, so if there are no more questions for now, if you have questions, you can upload them on Classroom anytime. So you can post them. You can use Classroom at your convenience. And all right, so that's the end of the class today, and I'll see you guys next Tuesday. Bye-bye.